Hello guys, welcome to my channel. My name is Reutman and I hope you enjoyed this video. And just for explain what's happening is going on here, I will start create one series that will help you to understand the quantum computer. I have been working and study, not working in real life, but working by myself to study what is quantum computer. I just have been in the classical computer for some years, and actually I am developing all new skills where we can see what is the quantum. Basically we have that big computers that we see in the internet, and inside we have the microscope, quantum working inside of these machines. Okay, basically the quantum show how the quantum device is performing the computation. Okay, well, we have just done the part of the quantum device requirement, the extreme environment such total vacuum, and the absolute zero temperature that is needed for these machines work. Now that we have understand what's the quantum, we just will pass for the next step, that is the simulation. Yeah, simulation is very important. We just will understand the simulation here, why the quantum computer will solve the nice problems for us. For example, there are dozens of mathematical problems that the quantum computer can solve, and solve exponentially faster than the conventional computers. Basically, computational, that the natural complex problems could not be solved by this conventional computer, but luckily we are very it's a very lucky to have the simulations, basically because simulations will help us to solve the problems that are being done without expand in the real world. For example, the modern works because of simulation, which can be process of testing out of ideas or creating environments before putting them to work in the real environment. Ideally, these forms of the basis of rapid prototyping is low cost, and which bring us to the computers first. Yeah. How here we can see the bridge. Yeah, is a real world physical bridge being simulated in the computer before to put this bridge in the real world. So basically, the computers can be programmed to simulate the physical acts or issues that it's happening in the real world, like bridges, like cars, like airplanes. We can be quickly test this before put them to manufacture and being a single thing. But more than this, we can simulate like stock marketing, trade strategy. We can simulate autonomous car, roads, electronic ships, design, and so on. We can simulate anything. We can, because it's more cheap and the effective way to reach the good solution for problems. But why we need to simulate atoms? Actually, not a real physical matter, but atoms and molecules that is much more small. Sometimes we can think it's just for research science, but no. The simulate molecules could be lead us to fast drugs development and new materials, like in the new materials, like in the, come on, get one fiction example that could be real, is like the Iron Man, where he discovered a new molecule and create a new molecule in the world. We can simulate anything before construct, and these new materials like clean energy production and transmission, food technology, and better understand the physical world that we are living actually. Yeah, so basically it's this. Also, come on, just pass we see the physical, classical physical, describe the actions of billions and billions of molecules, of existence of molecules that exist. We can, make it research, and each molecule by individual simulate them. Okay. But the question now that we came is here: why quantum? Okay. Why quantum? Is this the next step? Why quantum? So basically now I will share with you these guys here. Get it? Let's see if I can just put here. Yeah. Why quantum? Basically here we have the quantum, and we will understand a little bit why the quantum and why he's a killer on this, like this. But basically the quantum computer will be useful in many things, but the killer app is the modeling of behavior of the quantum world. Like we see, we need, since the molecules follow different rules, to those governing the computing device inside of large digital computers, it's difficult to predict how they will behave with the conventional technology. This kind of prediction applies for the quantum interaction, like atoms and molecules, and call it quantum simulations, and more natural for a quantum computers to tackle because they are too different. Build quantum is too. How I can explain that? Let me know. I'm not sure if I can explain very well this. If you don't understand, you can let me know in the video. I can make a little bit more, about it. But since the molecules follow the rules that is governing the compute device inside of large digital computers, it's difficult to predict how they will behave with the conventional technology. This kind of prediction applies to the quantum interactions of the atoms and molecules. That's called the quantum simulation. It's more natural for a quantum computer to tackle because they too are building different quantum physics. For example, this simulation of you are seeing here, the represented simulation of quantum physics, is a real challenge for the computers. We will understand a little bit more about this. For example, even they are so small molecules that contain a lot of information, too much information, that we try to measure that information using things like bits or bytes. Every new qubit added to a quantum system double the size, and the computer need to be simulated. This called the exponential growth that we attempted to do these things now with the conventional technology. Even though it quickly becomes impossible, because of the sheer importance of it. Your current simulation of a molecule properties are, for lack of a better word, fuzzy for this. Unfortunately, the nature of exponential growth of the information means improvements in conventional digital technology won't help. We need a new idea. The intuition of one of the founders in this field, the Dr. Feynman, was that the computer need to be built in the physical would be much better simulate quantum physics, but with a quantum computer, not with the classical compute. And he was right. We will understand why he was right. Because the quantum computer actually, he can have, good accuracy, but he will demand a lot of memory, In this case, the accuracy need to be remain high for the simulation to be used, In this case, we need to have high accuracy and low memory for this, and we will understand why. Okay. For example, for some applications, low accuracy simulations provide enough information to be worth the time and money and run them anyway, but high accuracy will be better always. Okay, we will have more details now that you can a little bit to understand this. And just for you understand, I will just put this image here for we understand the quantum and classical computer work in hybrid. For example, here we have 100%. We can have 100% of the quantum, for we get we can get indeed the explicit approach that will give us the better pixel, in the area of the chemistry. For example, a significant fraction of the world computer time is spent trying to simulate quantum physics and chemistry. It is the revolutionary potential of simulation new regimes in the chemistry that was lead many to suggest this is one of the most promising applications of the quantum computer. What's more, in the same potential application is the chemistry simulation that how we can see here. Maybe only require a modest size of quantum computer, like 10%, example, and we use the other resource of classic computer. Is maybe the first, application the quantum computer field. And in conventional computer simulations of chemistry are in the effect the pixeled pictures of the physical world. Information forming details of the interaction between atoms and molecules is not possible to even store in the digital computers, and let alone simulation. But the quantum computers are different because they represent quantum data using quantum device. This pixel doesn't occur the same way. Okay. Large quantum computers will allow shaper virtual pictures of molecular structures and interaction between them. Eventually, we may be able to create a complete virtual atomic world to simulate define details of actions and chemical transformation, or understand of both natural and synthetic materials. And the great thing about the quantum computers for this application is that we don't even need perfect clear image. Today, classical simulations are so bad that any reduction blurry can be a huge commercial technology relevant win. You understand? And because this is a great potential in the field of quantum for this area also. Possible. Now the part we have just to understand the why quantum. We just go now for this beautiful sphere qubit. We just will understand actually what is a qubit. Okay. Just for you understand a qubit, I will give you this image. Come on, put this image here. Here we have just the qubits. Come on, understand. The quantum information is richer than the conventional information. Now we will understand with this sphere. Whereas the digital information is measured with bits, and quantum information is measured with the bits or qubits. It can be with bits and or qubits. The fundamental unit of quantum information is the qubit that you have listened already. But the bit of information is either 0 and 1. But in the qubit is different. You want to understand. Information is more crowded and can be pictured as a sphere, okay? Like we can see here. For 1 bit or 2 or not or 1 qubit, we will see the big difference. Qubit will encode the quantum information. And to fully describe the information encoded in the qubit, we need to specify 2 numbers. Roughly describe how much the qubit is 1 or how much is 0. You need to understand how much is 1 and how much is 0. Whenever we represent a number in the computer, we will specify to a particular precision, like 32 bits is a pretty conventional approach. We have 32 bits. So to represent that state in qubit, we need about 64 bits. Okay, to represent the state of a qubit, we need 64 bit. Don't worry, if you are not familiar with this notion, I will explain better. This may sound pretty standard, but it's tricky. If you have a 32-bit, you know, it's a conventional approach that we have in the qubits and bits. Instead, just we need another 64 bits for each qubit, okay, which would be called linear scale that we speak before. The memory required to grow exponentially. 2 qubits will still required 128 bits. Okay, 2 qubits need 128 bits. Okay, 1 bit we need 64. 2 bit we need 128, the double. But the 3 bits we don't need. We need more than the more 64. We need the 256. This exponential growth double. 4 bits we need exponential in 512, you know. And for 6 we need 2000, you know, for 8 bits. I will put here just. In this case, for 2 bits we need require 128 bits. For 3 bits we need 256 bits. For 5 we need 512 bits, and for 5 we need 1064, and for 6 we need 2000 for 8. Okay, so basically is this the exponential growth that we will find in the bits for qubits. And by the time we have increased the 30 qubits, the work memory of the most of computers will be exhausted at only 27 qubits. The number of the bits required for matching this information will be more than all the data created in the world. It's like 300, zettabytes. It's a lot of information. 300 zettabytes. Okay, is there 300 zettabytes. This just for only 75 bits. That is a lot, We expect to have quantum computers with millions of qubits. You understand what this means? Millions of qubits. Never one computer, a classical computer, will arrive in this exponential capacity. A regime well beyond that the conventional computers could even hope to probe. It's where the opportunity of the quantum technology lie, Unfortunately, more qubits cannot be simply viewed as a more experience, how we can see here. The phenomenon of this is called entanglement. We will understand a little bit more after, which we will learn how this works in the quantum entanglement and how it's working in the quantum. Yeah. This sphere, basically, we have the qubit information, 1 or 0. You can explore the sphere by interacting and seeing there. We can see 0 or 1, but we have epsilon and x that could be any part of the sphere that we can flip, and this is the is the quantum information represented by this sphere. It's not just 1 or 0, but could be anything percentage between, the 0 and 1, and north, south, and any direction of the sphere. Okay? I hope you can understand this part. Now, I think it's interesting we understand what is good for. Yeah. I think it's interesting we understand what is good for, and I just will put here one basically picture. Come on, get it, this picture here. Okay. Understand what is good for. Here we have a map. Okay, the map. While many applications in the quantum computer will require decades to realize the potential for their use today, to give one small sample of the state of the art, here a few things of the research in the academy and industry of the quantum devices is used for. We can design new materials and drugs is one of the end goals of the quantum chemistry simulation that we have seen early. Optimizing transports and logistic network. We can be achieved this by encoded network structures and quantum interactions, and quantum computers also. We can search for the solutions faster using Grover quantum research simulation. We will see in this series about the algorithms and how the quantum computers could be used. Also, the area of pricing financial instruments is done by expanding up certain optimization subtasks, which can be bottleneck for large and scale problems. There are expanded using quantum combinatorial optimization algorithm. Managing risk and financial portfolios is one of the amazing area that you could be used by. You can be sped up by simulating market conditions faster or on quantum computers. Quantum Monte Carlo integration provide the expand up for this task is one application. We can improve training efficiency and artificial intelligence that is target through the increase of capacity of expensive power of the quantum data, and the machine learning that will set are huge, and demand a lot of resource like CPU. But there can be encoded and efficient in the state in the quantum in the state of quantum information. But in short, how we can see, the quantum computer have a potential to drastically improve the many different fields in the industry. While these applications are still in development, the people really don't have grow so much in the area, but have some real development with the big companies and big techs. We can see the possibilities really huge. Okay, a famous logistic problem is travel. For example, we can see here the map. We have one salesman. We have a problem. We can solve the instance of the problem by see these points and see the short way to he go in the which points, for example, Amazon, they need delivery most fast possible for any clients, And here we have, the complex, I will share here for you. Here, how you can see here, here is the shortest path that visit every node, need to be delivered and the short path. Okay, this salesman or Amazon, for example, need the quantum computer will here is a modest provide modest, but is important speed up for you understand the best node visit, and the best node visit that we can see it is this. No, is this, okay? Is the last one. Okay, this. Cannot pause here because it's a GIF, but okay, no problem. But here is the possibilities, that visit every node more fast possible, everything this calculation and the atomic way and physical way will be handled by the quantum computers. This is basically the concept what I'm talking about. Now we will see something that is very important. That is the, I will get it here. Okay, come on past that. Delete. We will see the quantum advantages horizon. Okay. Come on, get that image here and understand the quantum computational power and today's and the time area. In the future of the large-scale computers of quantum will be much faster for solving problems than the classical computers. Today, quantum computer could be used for solve many problems, but the classical computers are still faster. Okay, it's not any area or calculation that the quantum is faster. Putting these two factors together suggests a moment in the future where the quantum computer solves a real-world problem faster than any classical computer that actually is not exist, not is real. When it's secure, we will say we have achieved the quantum advantage. Okay. This is the quantum advantage when the quantum really solve any problem that a classical computer cannot solve. After that, we will truly see the exponential possibilities. Okay, we are soon to reach the crossing this point, showing this advantage. How we can see here, we have the quantum advantage. Here we have the classical era. We are here today. Okay. When you arrive here in this point where the quantum technology passed the point of the classical computer or digital technology, we are in the quantum advantage, okay? And we enter in the era of called NISQ, okay? We are today here, okay? In the area now, it's called NES key, that stands for noise intermediate scale quantum. The keyword here is noise. We only have small to medium-sized quantum computers because noise prevents us from building large ones. Okay. We will understand a little bit more this noise, and we can understand better, what's happened. Actually, we see we are the classical area that we don't have quantum technology. Today we started the noise. Come on, get it. That is a noise intermediate scale quantum. In this area that we are actually living, we not achieve yet the quantum advantage, but will be soon achieved. And to address this problem and accelerate this horizon of the quantum computing in advantage, yes, in this field, I am bring these videos and help you understand the quantum technology. Also, I am create projects in the area that is a software quantus that is will help to people understand and work in the quantum field. Okay, but the path forward is clear. We need more qubits. Okay, we will understand after about the noise that I speak about to prevent we actually create the better computers of the quantum. We need to win this problem of noise, and these need to be simultaneously great, you know. But good. How we can see here, we have the classical error that we have 1 qubit. We have the area that we are actually today, the noise intermediate scale quantum area, that we have 100 qubits, that actually the computers already arrived. When we are arriving in 10,000 qubits, we will have, you know, like a quantum advantage, that is the tomorrow, and 1 million of qubits is the future, is the quantum area. Okay. It's amazing, right? Predicted the future is a tricky business, but is there always how I can speak. It's always we have caveats and unstated certitudes, you know, that is not so clear sometimes. But the global effort to realize the quantum computer advantage drive us to the data sooner. Okay, guys. In this video, we have learned about the quantum computer. We get some activities just to recapitulate what we have seen. We have seen what is the quantum computer, the areas that he will use it, how it's work, the computer, why the simulation, why we need the quantum computer, because how fast he is, what is a qubit and how it's working, the difference between the bits, and some advantages about the calculation, simplified, and we see about the horizon of the quantum advantage, about the classical area, and we see the future of the qubits also when we are achieving millions of qubits. This is a quantum area. Okay, I hope you enjoyed this video. The next video I will talk about how the quantum computers works. It's a very nice video. We will understand really how it works, and you will understand how he solved the problems. It's amazing. You will understand it's not that thing of black box and magic thing, a trick that happen, but you will understand in really, you know, in the physical way how it's been studied and used. Okay. If you liked of the video, subscribe. If you don't subscribe, just give it a like and or comment something I don't like or I like it, whatever, you know, you can put whatever. And I just thank you for watching, and I hope you have enjoyed it. Have a nice day or night. Bye bye.